So it's my pleasure to introduce Professor Ravitej Uppu from the University of Iowa. Ravi completed his PhD in the Netherlands in the University of Twente in the COBS collaboration, where he was looking, as far as I understand it, at pretty much all things optical communications related, many different aspects, but I think specializing in wavefronts shaping. After which he came to Denmark to the Niels Bohr Institute, which is where I had the pleasure of working with him for a while, where he started to work towards getting the resources needed to put together some of these ideas that he'd looked at before into practice in quantum in using quantum technologies, using single photon emitters. And so I think that this is what he's going to be telling us about today, and I very much look forward to it. So thank you very much for coming, Ravi, and please take it away.
Thank you, Nir, and thank you for the introduction. So yes, today what I will talk about is about coupling emitters and single emitters and photons so as to perform hopefully useful tasks. For instance, what you see in the backdrop here is a cartoon rendition of how we would imagine a network of network for quantum communication would look like. So each of these blue boxes would be nodes, and then we would transmit some quantum states, preferably in photons because they are good in propagating over long distances. And what you see as these artistic renditions are like essentially photons that are entangled with each other in non-trivial entanglement forms. For instance, this would be a tree cluster, which is useful when you want to protect the information, even if there is a photon loss. For instance, this propagating down and some of the photons being lost can be regenerated and then transmitted further down in a quantum secure way. So going into all these quantum things, so let me first draw your attention to this word quantum advantage. So we do hear about this fairly often, but what do we mean by quantum advantage in the context of today's talk is essentially this this sentence where what we mean by that is that the ability of a system, of a quantum system, or I would say more specifically not a quantum system, but a quantum device, because it has a functionality. So it can consist of several quantum systems, which is built to perform a specific task. And it should be able to perform this task faster than a classical machine, than its classical counterpart would. Now, an example of these kind of systems, which are hard to perform in classical machines, are studying non-equilibrium processes in many body systems. So transient phenomena, which are relevant for studying how does a large molecule behave, or with several atomic centers. How does it behave? How does it evolve? Temporal evolution of it, and even for that matter, trying to find some specific conformational ground states of it. And while this sounds fascinating and what we would want to work towards, where do we sit at this point of time with realistic hardware is somewhere in the 4-molecule or 4-atom systems where we are trying to calculate the Hartree-Fock energies. So there is a big gap that we need to cover to do realistic technologies. And today what I will talk about is like, how can we realize quantum devices so that we can probably push towards these boundaries. So first, to talk about this quantum device, as I mentioned. So one could define a quantum device as something that has got a functionality, or where the functionality or principle of operation depends on quantum mechanical effects. While this captures the essence of it, this is kind of vague as well, because I could say that the chair that I'm sitting in, or the table, or the mouse that I'm moving around is also a quantum mechanical object, because if you go deep enough to the smallest scale, there's always quantum mechanical effects at play. So I would have to modify it to say that the device employs or harnesses quantum mechanical effects for its operation. And examples of such devices can be composed of several different quantum systems. It could be single atoms, or the things that we have probably seen in news more often, which are these flux qubits by IBM or transmons from Google. It could be even macroscopic scale objects like this membrane, which supports a mechanical mode that can, like, you can cool it to the mechanical ground state, and you can start observing single phonon operations principle if you can remove all the thermal energy in it. Or the more complicated object of the lot to see is photons, and that's why I make this drawing, which think about it as waves or particles, depending on how we interpret or how we use the system. So what are the questions of interest going forward if we want to implement photonic-based quantum devices? So the three questions that I would be looking at is, how do I realize a single or an entangled photon qubit? And what is the fidelity in generating such a qubit? In the sense, what's the quality with which I can generate? And whatever number I can put, I could call it 100% fidelity or 90% fidelity. And why care about this fidelity, right? So, and so the rationale behind asking these questions is, the first question essentially tells us about how well can these quantum protocols that I would implement scale? What's the efficiency of the source that is required? What if I create these, what are the accessible quantum information processing protocols that we would be looking at? The second one actually takes us into in a different direction, but a very interesting direction. It's about understanding the fundamental limits that are imposed on generating these states. So it's exploring fundamental physics. So it's in a way a very good motivation to generate the best possible qubit. And the third thing kind of ties everything together and say, okay, I can generate something at the best limits that I can, and I can generate it so that I can generate many of them. Then if I put them all together, then this fidelity bound that I could set essentially tells me what are the protocols that I can implement. And in the context of this, what I will talk specifically about are photon-emitter interfaces to generate photons. Now, to motivate why photons, it's just because it's simple to work with, and we can see the quantum mechanical effects right from this experiment, the hallmark experiment for observing quantum mechanical effects, where if you shine two single photons, identical single photons, on a beam splitter, then there are four possible outputs where the one which is incident from the left transmits, and the one incident from the top gets reflected, and so on and so forth. And because of the phase relation at the beam splitter and the fact that energy has to be conserved, the terms at the center get cancelled for identical photons. So so the quantum interference leads to a complete cancellation of these terms, so that we end up with the fact that these two photons are always bunched at the output. So they have to always leave from either the right output or the one which is going down. This is the celebrated Hong-Ou-Mandel effect, which is at the heart of most of the linear optic based, like essentially I just have beam splitters and phase plates and everything, and then I have single photons. And putting this together essentially gives me a quantum device. And one such quantum device, which we'll talk about in the context of demonstrating quantum advantage, is this special task of boson sampling. So what it is I have this collection of, as I said, I'm only going to talk about linear optics. So I have, as you can see, beam splitters, these cubes. I could have, let's say, some additional reflectors. I can have thin plates, which give me phase shifts. And I send in light into this network, and I get photons that come out of this network. This is the simplest scenario that we can think of. While I show this with green light because it makes a pretty picture. But what now think about not having this intense laser beam propagating inside, but single photons going inside. So mathematically, we can say that this complex network inside is implementing a unitary transformation because it's linear optics, so we assume no losses. So it's a unitary transformation. So n photons from input goes to n or transmits through the network and comes out of the network. And let's say we start with, there are m modes which are larger than the number of photons. And when I write this 1 subscript 0, then that particular mode 0 has a photon in it. Or if I say 0, then it doesn't have a photon in it. So he asked this very simple question. Now I sent these photons in this configuration. And then I asked this simple question, what is the probability of these photons arriving at different output ports? Or I can ask an even simpler question and say, will these n photons which I injected in come out at this specific port 1, port 20, port 30, and port 90? Now, this turns out to be a non-trivial problem, all arising from Hong-Ou-Mandel interference. So let me just try to recap Hong-Ou-Mandel interference as we just saw. So if I send these two photons, while they are represented with different colors or different shades, think about them as independent or identical photons here. So these two photons, now I'm interested in the fact that whether these two photons come out in output port 2 and 3. Now they have two ways of reaching it. Either 1 goes to 2 and 2 goes to 3, or 2 goes to 2 and 1 goes to 3. So there are two photons. So there are factorial 2 number of possibilities. And the probability that this state would occur is given by just the matrix elements multiplied and then summed together. So it's basically this submatrix 1, 2, 2, 2, 1, 3, 2, 3 submatrix. And this is what's called the permanent of this submatrix. Now, if I scale it up further, and instead of just having 2 photons, now I add 3 photons. 3 photons, there are factorial 3 number of possibilities. And if I keep scaling this further, if I have n photons, there are factorial n number of possibilities. And we have to take the sum of all these n factorial possibilities to get the probability of that specific, of the 3 photons, in this particular case, arriving at these three output ports. Now, the thing with this simple question is that on a classical machine, the best possible algorithm that we know about to calculate this permanent of this matrix is not super efficient. Whereas on a quantum machine, all that we need to do is to sample the distribution. Go with detectors, sit at the output, and build the distribution. So the best known classical algorithm, which is called Ricer algorithm, scales essentially like this. It scales as 2 to the power of the number of photons, which is, in other words, saying that this scales exponentially with the number of photons. However, there's this really nice result from Aronson and Arkhipov, which showed that the Boson sampler would work at in a polynomial speed. So it's n to the power of a being 2 to 5. So that's something to be, that there's like a lot of theory behind why it's between those two. So let's not go there. But the key takeaway is that it's non-exponential, which is amazing. So if we can actually implement such a system, we can actually show that this quantum machine, this boson sampling machine, would perform faster than a classical computer would in giving us the answer to these questions that we ask. But what does it take to demonstrate such a device? So the requirements that we are looking at is that we need n identical photons, because just now we talked about Hong-Ou-Mandel interference. So we need these n identical photons. We need a low loss network, and we need very high efficiency detection. That's just because losses in detection also will scale as exponential, right? Because if you lose a photon with 10% efficiency, then to detect 10 photons with this 10% efficiency, you'd have to take the efficiency of detecting, let's say 0.9 to the power of 10. It just keeps cascaded multiplying. So we want to ensure that these are all good. Now, the nice thing about photonic foundries is also that low loss optical networks are available. The scale of the network is another question, that is what is technologically feasible that can be made. But at least it's available, and we can do very, very low loss networks using industrial facilities, industrial fabrication facilities. And efficient detection is also something that uh, I would say for now, let's take it for granted. While I'll come to this point later at the day, but later in my talk. But the nice thing is that it's possible to generate several tens of detectors with this very high detection efficiency. So the key question that's left is, how do I generate this n-identical photon? So that's what I will talk about. And to get a perspective, a little better perspective about how many photons, right? So a very simple picture that kind of gives you a feel for where do we sit on this chart as to how many photons do we need to actually generate. So let me take you through this graph that I have. So on the x-axis, I have this number of photons. And on the y-axis is the number of computational steps required to calculate the permanent on a classical computer. Now, let me first draw your attention to these green, red, and blue lines, which I marked as 2000, 2020, and 2050. So this number tells us what's the capacity of the fastest supercomputer in existent in this particular year. So in 2000, we had a teraflop peak capacity supercomputer, which if we used, we can calculate a permanent of about 39 by 39 matrix. In 2020, so this was in last October, so that was Summit, which was at, so IBM Summit, which was performing at about 100 petaflops at the peak speed. That could do about 52 to 53 photons. That's taking into consideration that we are using the complete capacity and using the most efficient algorithm, right? And if we just keep scaling it further, even 30 years down the lane, we are still, let's say we just take the same scaling, logarithmic scaling actually that I put there, then we would be sitting at around 70 photons. But now let me draw your attention to the vertical lines on the x-axis that I dropped down here. So what these vertical lines, these years mean is the number of photons that we were able to generate in that particular year, identical photons. In 2003, we were doing around 3. 2012, there was this really nice article which showed 10 photons with very good efficiency, with good efficiency. Then this 2019 article, which showed boson sampling with 20 photons from Janwei Pan's group, was really good. And then this 2020 is something that we have been trying to implement with single-photon generation using quantum dots, where we could, in fact, reach a threshold here. So there are caveats and there are things that I will talk about later, because what do I mean by being able to generate these number of photons and whether it would outperform a classical computer or not. So we are looking at a pretty rapid scale up of the number of photons if we just look at the number of years that have passed. And likely we'd be able to cross this quicker because we just need to add one photon on the x-axis. On the y-axis, we have to add exponential degree of computational power to classical computer. So that's why it kind of is in a very exciting juncture, right? To think about implementing such a device and doing an actual demonstration of quantum advantage. And my choice of route that I've worked on was about using single quantum dots, which are coupled to these photonic structures. There's a laser which comes in, excites them, and then this emits photons. And as you can see, this emits like this photons on a string. So each one is emitted when one laser pulse comes and hits the quantum dot, and then it emits a photon. And the next laser pulse comes and hits, and then it emits another photon. And all of this can be extracted off the chip using these grating couplers. So these are the requirements that we talk about. So it needs to emit a photon every time there is a laser pulse that hits the quantum dot, that excites the quantum dot. And the next important thing, as we also talked about, is that the emission has to be coherent in the sense that the photons have to be able to interfere with each other. So they have to be indistinguishable. We shouldn't have losses. And we do not want more than one photon. That's just because it makes analyzing boson sampling so much more complicated. So that's low multiphoton. So every time it emits, it has to emit only one photon, not two photons, not three photons. So these are the requirements that we'd set out to do. And probably that's a nice point for me to break. And if you have questions till this point, you could please go ahead, unmute yourself and ask, because after this, I'd go into the actual device.
Is there? I didn't see anything in the chat, but maybe I can ask a quick question to start us off. So you said that the boson sampling on a quantum system scales like n to the a. Is that due to the number of times you have to run the measurement, or where is this number coming from? Is there a simple explanation?
Yeah, it's essentially the number of, so it's the way the quantum distribution, the probability distribution looks. So think about this as if you have the both the Hong-Ou-Mandel effect of two photons, then if you want to see the interference of two photons and that it would always end up in one port or the other, it's the same thing now scaled to n photons. So there are these special clustering of the probabilities that happen, right? So it's the number of times if you have to run and construct a distribution to see a difference from the classical distribution, like distinguishable photon distribution.
And does that assume that you have no losses in the system? So that
That
you're always measuring?
Yes, that particular case assumes that we are not looking at photon losses. So with photon losses, naturally, there will be an exponential overhead. And that's where the tolerances in the efficiency of the source comes in. So it needs a bit more complicated analysis from there to say where, where we need to actually hit with efficiency and indistinguishability of photons.
So so this is a bit of an unfair question to you, but maybe you can answer it anyways, because it's not about your work. But you know, when Google said that they hit that they've demonstrated quantum advantage using boson sampling, did they account for these losses, or was that not accounting for these losses?
That particular case was like, I mean, we are not trying to, at that point of time, comparing. It's not quite boson sampling, right? What they were doing, they were trying to do this randomized benchmarking test. Like, I would be more, it would be more easier to compare against what Janvepan showed in last year, the squeeze state photonic boson sampler. That's more in line, and they, with the squeeze state thing, they do have quite close to the efficiency that's required in a slightly different geometry.
So we have a comment that you could argue that with a boson sampler, you're just letting light do something. So the question we have is, how is doing boson sampling different from having light bounce off of things and taking a picture?
That is a very good question. And that comes back to the point. I never, in this part, when I said I want to demonstrate quantum advantage, I did not say whether I'm doing a useful task, right? So this particular task, specialized task of boson sampling, is purely to highlight the exponential speed up that's possible. Now, there are alternate ways where you can engineer the structure, the underlying unitary matrix, and also the way you collect the photons and what you're collecting on, which can be used to implement photonic quantum simulators. So that goes in a slightly different direction, and it's more involved. But indeed, what we are actually doing is just shine the light into a network and let it do its thing. But we try to control how it does its thing inside the network and then make a detection.
Is this not also letting you in some way calculate the permanent of a large matrix, which has uses in many other network schemes, and is not efficient at all on classical computers?
Calculating a permanent is a very complex question, right? Because if you want to calculate a value, then you need to start talking about, okay, what's the error on this particular permanent of this submatrix that we are putting? That's not what boson sampling does. That's why I said the good question to ask is only whether that particular state occurs or not. While in a classical machine, you have to calculate the permanent. There is no simple way to do it. In a sampler, you don't have to ask that question. And that's where actually, subtly put, actually, that's where the advantage lies, because it's about the question that you ask the system. It's the same thing with simulation. If you want to ask whether a specific configuration of a chemical state occurs or not, is that, and then the next question would be like, okay, what's the what would be the ground state energy of such a state? Now, so that's the difference between the two questions, and both can be done, but the second one is more difficult.
Right. So I think there's no more questions at this point.
Okay, brilliant. Then I will continue. So, so the choice of implementing these n identical photons was to use quantum dots, and in particular, looking at so what quantum dots are is that essentially they are one semiconductor material embedded in another semiconductor material, and they have a very finite size, small size. In this particular case, it's 5 to 10 nanometers in size. And what they do is you can essentially create a electron hole bound pair, either optically or using or electrically. In this particular case, we'll talk only about we can optically excite an electron hole pair. By what you are trying to do there is on this graph. So you have this valence band of indium arsenide, which is a narrower band semiconductor in comparison to gallium arsenide. So you have this potential well. So you excite one of the electrons from the valence band into the conduction band, and then when this electron and hole recombine, it emits a photon. That is our source of single photons. Now, if we were to just place this single photon source in free space, it's going to emit all around uniformly, and it's a pain to collect that. And that's where the trick comes in. Now let's start putting this inside a slab. And this slab has certain, so this is, you have a high dielectric and a low dielectric embedding this high dielectric material. So we can engineer the thickness of the slab, and you can guide the light to go propagate just within the slab. So instead of now propagating all over the place, we have the light propagating in the plane of the slab. So we are restricting some portion of our K space, or wave vector space. I can do a little bit better by cutting that slab even further. So I'll now cut the slab also in the horizontal direction, or the lateral, in the plane, so that it has a finite width of the order of the wavelength of light, and also height. And by doing this, and by placing the emitter inside, in this particular case, I'm showing it in silicon and silica, but in our case, we'd be doing this in gallium arsenide. We can control the way this emitter would emit, that we can force it to emit in this one optical mode of this waveguide. So think about this as a fiber. And on top of that, there's also additional control that one can get on the spontaneous emission rates. I will not go into that because while it's very interesting, and it's another part of the work that I did at COPS in Twente. So there, now we want to go a little bit further and say, okay, I want to actually not just make a slab waveguide, but utilize the features of photonic crystals. What's the feature of the photonic crystal is that by making a periodic array of holes, we can create a stopgap for light. That is basically saying that if an emitter were to sit in this range, then it would not emit at all in an ideal case. And then start taking this particular photonic crystal and remove a row of holes. Then what this does is that within that gap, the stop gap, there'd be this additional modes that we see. And we are particularly interested in the lowest frequency mode. And so by coupling the light into this particular mode, we can make the light propagate, or rather ensuring that this particular dipole overlaps with the electrical mode or optical mode of this waveguide, we can ensure that the light selectively propagates like the cartoon that I showed. So now the quantum dot is coupled to that particular optical mode, and then whatever it emits is essentially propagating down that waveguide. And to quantify how well does it couple to that waveguide mode, so we can say how much does the quantum dot emit into the waveguide mode. So that's this gamma WG. Now a portion of this, because there can always be imperfections, portion of this could also be that it could scatter out of plane. So that's this non-guided modes. And then the third thing, quantum dots are never really ideal systems. They also tend to have processes where now we created this electron hole pair. Now, for some reason, this electron decides to jump out of the quantum dot, let's say, or it changes its, or it becomes in, or it transitions into a dark state. So all of these can happen, and that's what's captured in this non-radiative rate. And to quantify what's the single-photon coupling efficiency, so that's given by this beta factor, which is the ratio of the light that is radiating into this waveguide mode to the total rate that it can. And we would want to make this beta as close to unity as possible. Now, this is a number that has been shown to be possible experimentally, and typically in the sources that I will talk about, this is in the ballpark 90s, in the 90-92% level. Now, the nice thing about putting this emitter into this single mode waveguide is also something that near works on, is that there is a strong photon-photon interactions that we can introduce. For instance, if we were to take this single emitter, a single two-level emitter in a waveguide, and shine photons into this waveguide. So there's this light which is propagating from left to the right. Then depending on whether we are shining a lot of intensity or down to the single photon level, the transmission of the light through this waveguide is affected. So if we go to the level where we are shining just single photons, the transmission drops to near zero, and that's because the re-emitted light and the forward propagating incident light interferes destructively to cause most of the light to reflect back. So if we were to tune, now this is going to be dispersive because this is defined by this dispersive mirror, which is this quantum dot or this emitter, the two-level emitter that's sitting. So right on resonance, so the x-axis now is the frequency of the operation of this quantum dot. So right on resonance, we would see this thing happen. Whereas if you go far off resonance, it basically just transmits through because it's not interacting with the quantum dot. Now, this is a feature I just wanted to draw attention to, because this is something that we use to find the quantum dots. Now, how do I locate all these quantum dots that are coupled to this waveguide? Because it's a big device, or big by 20 micron device. So what we do is we actually shine laser into one side of the waveguide and collect light at the other side and just scan the frequency. So, and then a typical trace looks like this. So you have several of these dips. While they look like noise, it's just because I'm scanning a very, very, very broad range. Each of these dips that you see corresponds to a single quantum dot transition. So for instance, if I highlight this particular line here, so you can see that if I just zoom in there, then you would see this particular one, which has a dip going down to about 40% deep or 60% deep or down to 40% transmission. And then this one can also be zoomed in, and then you would see a different depth and width, because quantum dots tend to be very inhomogeneous in their properties. So that's the first part. While I did not tell you how good it is, the thing is, the fact that you see this very strong interaction of this quantum dot with the photon kind of tells us that, okay, we have a very well coupled quantum dot to this single waveguide mode. And then generating a single photon is again a bit of a non-trivial task, because you have so many different configurations of excitation possible. One simple thing to create carriers is to excite in the above band regime, but then this causes a bit of a trouble that there is additional non-radiative decay channels, which adds to the jitter in its emission, which means that think about this as like if there is jitter, you Fourier transform it, it's going to come up in its spectral in its spectral line shape, and we do not want that, and that's part of the reason why we choose to do exact resonant excitation, which means that the laser is exactly resonant with the single photon emission. Now this kind of makes our life a little challenging. So the wavelength of the laser and the wavelength of the quantum dot transition that we are interested in is exactly the same. So imagine that, let's say I have a horizontally polarized emitter and the laser is also horizontally polarized, then we are basically just going to be swamped by the laser photons. So when you have to collect and excite from the same point, people typically try to do this. They go with a diagonally polarized laser and then collect in the anti-diagonal polarization. That way you can reject all the laser out and collect part of the light. Well, theoretically, this would give you about 50% of the emission that you can collect because the other 50 is rejected by our analyzer. But the nice thing about these planar devices, as I showed here, is that I can excite the quantum dot far, far, far away from the point where I'm collecting it from. So in this particular case, this is almost like around 20 microns away from the point of collection. Then all that I need is a confocal microscope. So I excite at one point and then use, because if the microscope has enough field of view, then it can collect from a different point. And basically you get this spatial separation of excitation and collection, and that gives you very, very strong suppression of laser. Theoretically 100%, never really there. We are looking at part per 100 or better, between part per 100 to part per 1000. So that is one single photon to, or one laser photon to 1,000, 100 to 1,000 single photons that are collected. And now if we basically excite this quantum dot with pulse lasers and then look at the output intensity that the quantum dot, or the number of single photons that I'm detecting on a detector, on a single photon detector, and I keep increasing in this particular case, I'm increasing the laser power, changing the pulse area. So you'd see a very nice Rabi oscillation. So going from, it's basically, I'm fitting this to intensity to this function, which is sine square of the pulse area. So at pi pulse excitation, so we reach detected count rates of about 10 million photons, which is, this has been corrected for detected nonlinearities and all that. So we actually have about 10 million photons in the fiber. And we went back and carefully tried to analyze where do we, and this is when exciting at around 70 million photons per second. So when you just look at it as the bare number there to what I have, it's 10 over 70. So that's about the efficiency that we have. And most of that loss then actually happens in the cryostat. And that's something that you're working on trying to improve as well. But we can actually go ahead and try to extract the efficiency of the source if we were to fix the optics in the cryostat. Well, dirty optics are a bit of a pain. So that part talks about the generation of the single photons, and now about generation of emission from the quantum dot. Now, the next thing that we are interested in is like to answer the question about how good is the single photon source. So first characteristic is how good are the single photons? So how much is the multiphoton character to the emission? And this can be done using this Hanbury-Brown twist experiment. So you take quantum dot emission, shine it on a beam splitter, a 50-50 beam splitter. And on each port, we place a photodetector and look at the coincidences. So when there is no delay, so basically you're looking at this, but the same event, then there's a strong suppression of coincidences, which means that two photons do not arrive together at the beam splitter to start with, because then they could split and there would be some probability of detecting them. So that's a good indication. And if I compare this against, let's say, what's the probability of generating a photon now to what's the probability of generating a photon in the next pulse, which is what the second peak here shows us. So the ratio of these two gives us the normalized G2 of 0 value of about 0.015 or about 1.5%. So that's about the amount of multiphoton emission that this source had. And that answers now our question about efficiency and question about the single photon character. Now what's left is how good are these single photons? Now I have this whole chain of single photons which are being emitted by the quantum dot. Now we want to know, let's say the emission 1, emission 2, emission 3, emission 4. We want to know how identical is emission 1 to emission 3 or emission 4. And this can be done by sending the light into this asymmetric interferometer. So what it's doing is, so there is a beam splitter here, or a polarizing beam splitter in this particular case, because we want to control the splitting ratios precisely. So there is a short path on the top or a long path on the bottom. And there's an extra wave plate here. And these short and the long paths interfere at a 50-50 beam splitter. And we try to do a Hong-Ou-Mandel interference of the photon that took the short path and the photon that took the long path. Now, let's say our first photon takes the long path and it spends exactly 1 delta t. Then the photon, which is generated after delta t, takes the short path and then so they arrive together at the beam splitter at this point. So the first photon and the photon generated after delta t. Let's say delta t is 1 laser pulse excitation. So it would be the second photon that arrives here on taking the short path. And to ensure that they are identical, we can control their polarization on the second path. And we can then do 2 measurements where we have when they are perpendicularly polarized to each other, which means they are distinguishable photons. So then we'd see coincidences which are high, because they can, each of the photons can independently take the path that they want. Whereas when we make the polarization parallel to each other, that is, both the photons are perfectly identical, or should be perfectly identical, then they would we'd have Hong-Ou-Mandel interference of the two, and we should see a suppression of the coincidences. So here I show for 2 different cases of delta t. So one delta t of 13.8 nanoseconds, which is essentially subsequently generated photons. Another one at 786 nanoseconds, which is the 100th photon. In this particular case, this would be second photon. This would be the 100th photon, 115th photon that's generated. And you can see that they are closely similar to each other. And if I calculate the amount of suppression of coincidences, which is called the photon indistinguishability, and make a plot as a function of delta tau, so the time difference between emissions, then all the way up to 115 photons, we see a photon indistinguishability of over 96, about 96.5% across this whole string of single photons. So you have 115 photons that are being generated, which are almost perfectly indistinguishable, almost there. So that's quite exciting. So just to summarize, so we have essentially really low multiphoton character. We have very good indistinguishability. And as I said, after factoring out the inefficiency of purely the optical part, which is possible to get rid of, which is something that I'm working on now. So it's possible to reach a source efficiency in excess of just about 80%, 80, 81%. And that is being realistic in the sense that I do consider the losses that putting a spectral filter would introduce. I do consider the losses that you would have with a fiber coupling efficiencies and all these things. So it's being realistic. We could reach source efficiencies in excess of 80%. The thing is, like, sure, I have now a chain of single photons, but how do I go about using that? Now, the way to use this single photon stream is to switch them. So I switch it such that to convert from this temporal string of single photons, I can use a set of switches. So think about these as railroad relays. So the first photon is let through all the way through the switches, and then it ends up at this long fiber loop. The second photon is switched by the first switch into this second longest fiber loop. The third photon is switched at the third longest fiber loop, and so on and so forth. And by doing that, we can ensure that all the photons arrive at these different spatial modes together. I can do this super efficiently with an efficiency per channel efficiency close to 90%. And it seems I'm at 45 minutes. So I will not go into details about boson sampling and how this works with more photons and all that. But let me try to summarize what this means. So all these imperfections, as I said, this indistinguishability is not perfect. This is what we wanted with single photons, and we discussed earlier. Now, having photons which are not perfectly similar to each other has to impact our interference quality, right? And to capture that, what we have here on this plot is what's called as the trace distance. What it's telling us is how different is the distribution, the probability distribution of the events. How far is it from the perfect case? So if we are at this bottom at 0, then we are very similar to the 100% case. But you can see that even adding 2% indistinguishability of each photon already takes us about 20-25% away. And in this particular case, we are looking at around 60% away. And if you have sources which are 80% indistinguishable or 20% non-indistinguishable, this is already pretty bad. They look, for a 50 photon interference case, like what we talked about at the start. So if you have injected 50 photons in, it pretty much just looks like a classical sampler. There is no difference between indistinguishable photons or distinguishable photons interfering there. Now, the thing, after a lot of analysis, which you can read about in this article, what we actually managed to conclude is that with the source performing at this indistinguishability and the given level of circuit efficiencies and the performance quantifiers that we have, is just sufficient to cross the threshold of this quantum advantage, that if we use such a source in a realistic network, we could potentially demonstrate boson sampling at speeds comparable or faster than a classical computer. That would be very exciting to do it, as long as we have enough money for all the detectors and the circuits and the photon sources. But that would be a great pitch for people with money. So yeah, but going further, as my own group here, my interest is largely on going beyond single photons and generating large entangled states. And part of this is also something that I've been involved in at the university to start a photonic quantum simulator like platform. This is sort of something that we just got a seed grant from the university, trying to bring together the departments of physics, chemistry, and math and engineering, looking at properties like semiconductor growth, spin-photon and 2D quantum dot interfaces, and ultrafast spectroscopy, benchmarking chemical calculations, and on the math side, looking at mapping and scalability and error mitigation schemes. So this is sort of like the kind of the whole infrastructure that one needs to go from something like demonstrating quantum advantage boson sampling to actually creating something that's interesting. And that's indeed that's a nice point for me to stop and take questions from all of you. Yeah, great, thank you.
So I'll clap for everyone. It's a little, I know, always a little odd with these
Yeah, Zoom
remote colloquia. So do people have any questions, or can I start? I'm always happy to ask a few questions. Okay, so let me ask a question while people think about it. But if you have a question, you can please just put your hand up, and I'll call on you to ask. Or if you see a pause, then you can just unmute yourself and ask. But so you said you needed 51 or so photons to get to this quantum advantage. Can you do something useful with one of these simulators? I assume you can do it with less than 51 photons, or is that not true? Because then you could do it with a classical computer anyways. So what is the benchmark for doing something?
So yeah, that's a very good question, because so when we analyze this whole quantum advantage, that's why I would say quantum advantage through boson sampling, right? Because the requirements for doing simulation or this term of quantum advantage is very specific to what's the protocol or what's the task at hand. Now, I can't give a immediate answer about what's the resources that's required, because that's something that we are currently working on, from these imperfect qubits to mapping to, let's say, a simulating platform. So what's the resource requirements given because we know what's in imperfections with our platform that we have, right? So utilizing these and trying to put things together to say what's the requirements. Yeah.
Okay, thank you. Mark, I see that you have a question, please.
Yep, very nice talk. I was just wondering what's your limit on the indistinguishability? Is it a timing jitter, and if so, is timing jitter part of it, or is it differences in the quantum dots, or what exactly is that?
Yeah, that's a wonderful question. So at that point of time, when we reached 96%, it was partly some timing jitter. And we can do better than that to the level that we would be eventually limited by only the phonon noise, the elastic phonon noise. And that would be at around 98 to 99% at the 4 Kelvin. And in fact, we could improve on these results after all this work. But naturally, there is this question, right? So what is realistically available in the lab? Like how good a laser suppression can we reach to have actual tabletop sources with, can we reach 98, 99%? So that would need more suppression of laser. So 96%, I'm typically quoting 96% because that includes the laser background. So that's the realistic number at the moment. So if you can suppress the laser further, then yes, then we should be looking at 98 to 99 as the fundamental limit.
Is the issue that each laser pulse is not identical, or that there's still some quantum uncertainty as to when you exactly emit?
No, the issue is purely optical. So we couple the light from the free space mode, right? So, and we imagine that there is no scattering whatsoever into the waveguide. But that's not the case. Like, in fact, that's something else that I was working with Willem Vos in Twente about how much light does actually get coupled through the unguided channels in a photonic crystal into the photonic crystal modes. And that's the fundamental limit. And in fact, I believe there are ways to reduce this. And that's why I would say the limitation is purely optical, just laser scattering, coherent laser scattering, which interferes with the single photon.
Oh, okay.
Yeah.
Thanks.
Yeah, that's a very good question. Do you see there being nanophotonic solutions to this, or wavefront? Like, do you control the laser pulses that you're exciting with, or which way do you go to get to 100%?
So this way, this is one way, right? So here this is this work from earlier this year with COPS. So where engineer the wavefront out. So you control the phase of the light that's coming onto the photonic crystal. So that's one way. So here I was using an external spatial light modulator to do that. But photonic solution to that would be using like a metasurface to engineer the phase locally, and then so that you can destructively control the scattering of, or at least reach a phase where you can interfere the two better off and reject the laser.
Okay. I have one more question, and then if nobody else can think of or has anything that they want to ask, then we can end it there. But just sort of quickly. So as I think of scaling this up, do you think that it will be better to take, if I want 100 or 1,000 photons, to have a quantum dot that's making 1,000 photons? Or would you want 20 quantum dots that are making 50 photons each? Or is there any way to figure out the right routes to go to?
Yeah, so that's a very important question. I don't think the using a single quantum dot and then keeping on dividing that to reach n photons, while it's not impossible to do this, so the limit comes from two factors, right? So when you so there is a repetition rate, maximum repetition rate for the quantum dot given by its lifetime. When we are switching, we are reducing it by the number of photons that we are generating, so linearly reducing it. But then to switch that, we are using a second circuit which has an efficiency. So if we can generate n photons using n sources, is always going to be better, as long as all the sources are nearly identical. So at least the degree of indistinguishability between the sources should be smaller than or equal to the efficiency of the demultiplexer. If we can reach that regime, then it's actually better off to just have independent sources.
And so if I wanted 20 photons, what am I best off doing today?
At the moment, to switch.
Okay.
Yeah, unless we can make two photons interfere with each other at 90%.
Okay, well, thank you very much. Are there any last questions? If you want to talk to Ravi a little bit more informally, then please just stay on the call. Otherwise, please join me in thanking Ravi one more time for the very nice talk.
Thank you.
I hope that everybody has a nice weekend. And Ravi, I don't know if you know, but in Canada, this is our Thanksgiving. So.
Oh, okay. Have a nice weekend.
So with that, I'll say goodbye to the people.